In this part of the lecture, we will learn the test of independence when we have a row factor and a column factor. Previously, in the earlier part of this chapter, we considered the test of in contingency table for the test of homogeneity. This one, the test of independence, you will see soon that the test statistic is identical to those tests for the homogeneity. Even though the two scenarios are not the same situation. In this one, the test for the independence, we are thinking about just one population in mind. And for this one population, we have a row factor and a column factor. And for the row factor, it's listing the different levels of that factor. And for the columns, each of the column lists one possible level of that column factor. For example, we might be considering the people watching national news on TV, and we could use the different use a factor to designate the network. So the network itself is a factor, and then the different network, ABC, CBS, NBC, or PBS, and so on. These are the different levels of the network. So imagine you have this in a row, and the column, now we're considering such as political philosophy, whether a person is liberal or moderate or conservative. And what we consider is for each of the individual being considered, this individual would be in one of the row factor and in one of the column factor. It would be exactly one of the row factor and exactly one of the column factor. So like at any time, one person could not be watching multiple networks. And this person's political philosophy is also just one of them. So that's this situation that we are considering. So we have two factors. One we put in a row, the other we put in a column. The observed values are going to be the count of individuals that falling into the row factor level I and the column factor level J. So Nij would be simply the count in this I and J's I's row, J's column. And when we put all these rows and columns together, what we get is a two-way contingency table. And this table will look exactly like the one we had earlier in the test of homogeneity situation. But the difference is that in the previous case, each of the row, we first predetermine the number of individuals that we're going to select out of that row. Each row represents a population, and we determine a fixed number of them to select out of that population, like N1 dot, that's a fixed predetermined value. Similarly, N2 dot is like the predetermined value, the number of individuals who are going to sample from the second population. So all the rows in the test of homogeneity situation, the total count in the row was fixed. In each row is fixed, okay? But now, when we are considering this test of independence, those row counts are no longer fixed. Instead, they become random, just like all the column totals. So in this case, what is fixed, that's the overall total out of both the rows and the columns. And the row totals will still denote with the same notation, N1 dot, like N2 dot, and so on. And the column totals, we will still denote them as N dot J, like N dot 1, N dot 2. And therefore, if you could recall how was the previous table written, that table will still apply. For this test of independence, our interest is different from the previous case. So what we care in this case is that the row factor and column factor, do they seem to be unrelated to each other? In particular, are they independent of each other? Recall when we try to perform a test, we would always consider under the null hypothesis what will happen. And if the null hypothesis does not hold, then what will happen? So we will consider composing a test statistic by coming up with two quantities, one under null hypothesis, the other one does not require the null hypothesis to hold, and compare these two quantities. So for this case, if the null hypothesis of independence is true, in that case, we would be able to write the cell probability. So like the ith row, jth column, that cell. What's the probability of an individual being selected out of the whole population falling into that cell? This probability can be written as the product of the row probability and the column probability. What I mean is that if we look at this one, the P sub I dot is talking about the ith row. We simply accumulate all the probabilities in the ith row, and that's the probability of an individual that's in the ith category of the first vector. Similarly, for the jth column, we can also look at what's the probability for an individual that falls into the jth category of the vector 2. So we use P dot J to represent that. Pi dot and P dot J, both of them represent just the probability for the one factor taking a specific value. And if they are independent, let's say, when we write this joint probability of an individual belongs to the ith row jth column, individual, okay, belongs to the factor, the row factor taking the ith factor level and the column factor taking the jth category, then this can be thought of as the intersection of two events. One is this individual has a row factor level I, and another event is that the individual has a column factor level J. And these two events, once they are independent, then the probability of the intersection between the two will be equal to the probability of each one of them. So probability of the individual belongs to the ith level of the first vector, and then times the probability of the jth level in the second vector. That's if the null hypothesis is correct. So with this null hypothesis, we are able to write the joint probability of an individual in a cell ij as the product of the two of these marginal probabilities. The row probability belongs to the ith one, and the column probability that belongs to the jth column. Due to that, our estimate for the cell probability P sub ij, that's the individual falling into this cell that's in the ith row and jth column, then this probability is simply equal to the product of the two, P sub I dot and P subscript dot J. And that's the probability. Now consider expected number of individuals that would be in that cell, falling into that cell. This expected number, we would think of it as, how do we consider that? You can think of this one cell versus not in this cell. If any individual being randomly selected, this individual must either be in that cell or not in that cell. Therefore, given the total number of individuals being a little n, then those that's going to be into the cell, falling into the cell, the expected value would be the n times the probability for the cell. And therefore, it's n times this P I dot times P dot J. Why it is the n times the probability? That's because when you consider just in the cell versus not in the cell, those are the two categories, and the total count is fixed. And now we are considering any of the individual, it's either in there or not in there, and these individuals are all identically distributed, so it's a binomial random variable. And in the binomial distribution, the expected value is always the number of trials. N here refers to the number of individuals times the probability. So N times this probability gives us the expected count in that cell. And this is assuming that the null hypothesis is true, such that the row and column factors are independent. When we are making the statistic, we would want to also consider the situation that the null hypothesis does not hold. In that case, we will be doing the observed count, which contains whatever is the relationship between the row and column vectors. So we will compare the observed count with the expected count. Okay, just now I was saying that N times this will give us the expected count. But the expected count now rely on the row probability in the ith row and the column probability in the jth column here. These two are unknown quantities, so we will need to estimate them. With this situation, all we know is that the row I contains all of the individuals in that row. It does not differentiate between the different columns. Therefore, the Pi dot, that's a probability that can be estimated based on the sample proportion of individuals in the ith row. So referring to individuals who has the first factor taking level I, little I. So Ni dot divided by N, this is the sample proportion of the number of individuals, proportion of individuals that has a factor level I from the row factor. And this is the maximum likelihood estimate, as we learned in the chapter 6. Sample proportion give us a maximum likelihood estimate of the population proportion. Similarly, when we want to estimate the probability that an individual belongs to the jth column, then we just need to use the total count observed for the jth column divided by the total number to give us the maximum likelihood estimate. So it's N dot J divided by N that give us this column probability estimate. Now we can use the sample size here, like here, the sample size N times the two estimated probability to give us the expected count. As we put them together, you can see that the two of the little n in the denominator and one of the little n that's outside will cancel one of them. So in the end, the expected cell count is simply equal to the row sum Ni dot and times the column sum of the jth column N dot J, and then divided by the total count. And this expected count was exactly the same as the previous situation when we test for the homogeneity. And this ratio gave us the expected cell count. So we have expected count now. The next is to combine the observed count and expected count together to look at the deviations from each other. Again, we will look at the squared deviation between the two. And divided by the expected cell count, that would have a chi-square distribution. For chi-square distribution, we will have a degrees of freedom, and this degrees of freedom, in this case, we will still use the general rule of thumb to use the number of free available values minus the number of those that's being used to estimate some unknown parameters that will give us the degrees of freedom. So in this case, how many free values do we have? If we go back to the table, in the table, we have the ith row, I rows and j columns. Recall here, the total number of these, each one of these count, we can just change them because all we know is that the overall total here is, if I'm going to put a total there, This n is the only thing that's fixed. This n is fixed. And in each cell, we will have the random number falling in there because each individual is randomly, each individual falling into each cell, that's a random event. So in this case, how many of the free values there? Total of I times j of them, but since we have a summation of all of them being equal to a single little n, therefore the total number of free values in this table is I times j minus 1. So that's the total number of free ones, I times j minus 1. And how many of them did we use to estimate the unknown parameters? So we used this first one divided by n to estimate this p1 dot. And similarly, we use the second one, n2 dot divided by n to estimate the p2 dot, and keep going. But are we having all n of them, for all I of them? The answer is no, because this p1 dot, p2 dot, and up to the pi dot, all of them together, if you add it up, that's going to be definitely equal to 1, simply because n1 dot, n2 dot, up to the ni dot, the total summation is equal to n. So even though we estimated I of them, eventually only I minus 1 of them are being estimated. The last one is actually determined by previous I minus 1 of them. So the total number of degrees of freedom that we use to estimate these row probabilities is I minus 1. Similarly, when we try to estimate the first column's probability, we're using this n dot 1 divided by n to estimate the p dot 1. So that's using 1 degree of freedom. And similarly, when we calculate estimated probability of individual falling into the second column, that's also using this second column count divided by n. That's another one. As we move forward until we get to the last one is actually just 1 minus the rest of the p together. So the number of parameters that we really estimated for these column probabilities, that's j minus 1. So in the end, how many did we use? We actually used the I minus 1 for estimating these row probabilities, and we used the j minus 1 for estimating these column probabilities. So together is the I minus 1 plus the j minus 1. That is I and j, I plus j, and then minus 2. So that's the number of degrees of freedom that we use to estimate the unknown parameters. So we use the I plus j minus 2, that many, to estimate unknown parameters, and total number that we have was on previous slide, that was ij minus 1, and therefore the free ones is the difference between the two, and you can easily verify it's simply I minus 1 times j minus 1. So that gives the degrees of freedom. This degrees of freedom happen to be exactly the same as the situation that we test for homogeneity. So you see, the test statistic is identical, and the degrees of freedom is also identical. Therefore, in fact, for this test of independence, we could just apply the same test that we have learned in the previous part of this chapter. So it's the chi-square test with the I minus 1 times j minus 1 degrees of freedom. The only difference is the null hypothesis and the research hypothesis is stated differently. In this case, the null hypothesis specifies that the row and column factors are independent. So the cell probability P sub ij, that's the cell probability, is equal to the row probability from the ith row and the column probability, the jth column, product of the two. And the test statistic is still the sum of the squared difference between the observed and the expected cell counts and divided by the expected cell count. And we use the chi-square distribution with the I-1 times J-1 degrees of freedom to determine whether the calculated test statistic is too extreme or not. So-called extreme, again, if the null hypothesis is not true, our observed and estimated would be different, and the squared difference will be big. Therefore, big values of the test statistic indicate that it's more extreme or evidence against the null hypothesis. So we'll try to reject the null hypothesis when the calculated test statistic is too large. How large it is, we'll try to use the p-value to decide. Again, p-value refers to in this case would be the chi-square distribution with the I-1 times J-1 degrees of freedom, and this distribution to the right of the observed test statistic value. That would be the p-value. Let's see an example of this. The table on the next slide will give us two factors of a population. One factor is about the paternal education, so that's about the father's education, completed the university or partial university, secondary education or partial secondary. So that's the different education levels of fathers. And then the column factor refers to the neonatal weight gain percent quantiles, like first quantile, second quartile, and third quartile and fourth quartile. We would like to see whether the father's education and the newborn baby's weight gain are related to each other or not. So that's our goal. And here's the table. In this table, observed cell counts are first listed, and then the expected cell count were already given next to below the observed count. For example, E1, Q1, this cell, we have 422 individuals in that cell, and 411.63, that's the expected count in that cell. When we try to consider contribution of this cell to the test statistic, we'll take the difference between the two numbers. So 422 minus the 411.63, and then we square it. Afterward, we divide it by 411.63. And this gives us the value of 0.261. And similarly, we can compute it for the second column in the first row, and then the third column in the first row, and so on. And in the end, we add up contributions from all the cells in the test statistic, and that will give us the statistic value. For this case, the statistic value turned out to be 19.016. With this value, if we want to use the chi-square distribution, we would do with the chi-square, and that distribution has degrees of freedom is I-1 times J-1. Since we have 4 rows here, I equals 4, and then 4 columns here, so J is equal to 4. I-1, J-1, that means 3 times 3, so degrees of freedom is equal to 9. So chi-square distribution with 9 degrees of freedom, and we'll try to look at the probability to the right of 19 in the chi-square distribution with 9 degrees of freedom. This probability, 19 versus 9, we definitely know that the 19 is bigger than 9. And in the chi-square distribution, the mean is equal to the degrees of freedom. So in this case, 19 is bigger than the average for the distribution. But how big is it? I mean, even though it's bigger than the average, but we still want to know how much chance it is to observe 19 or bigger in the test statistic if null hypothesis is true. So we can compute the p-value. P-value in this case greater or equal to 19.016 with 9 degrees of freedom. if you can either use the table or otherwise you can also use R to compute it. If you use R, it's 1 minus P CHISQ, and then the statistic value 19.02, and then you put the comma and the degrees of freedom afterward. So that gives us the p-value. In this case, 0.025. So with 0.025 as the p-value, we would consider the significance level, for example, 0.01 or 0.05. If it's 0.05, then this p-value 0.025 is less than the significance level. We will reject the null hypothesis. But if we use significance level 0.01, then the p-value is no longer less than the level. Therefore, if 0.01 is the significance level, we cannot reject the null hypothesis. The 0.05 or 0.01, those just reflect a user's comfortable level of how much chance do you think simply by random you can accept that to happen if null hypothesis is true. When using 0.05 as a significance level, that means allowing a 5% chance of mistake if null hypothesis is true. And if you give 0.01 as significance level, that means when the null hypothesis is true, you are only allowing about 1% of chance to be mistake. So depending on how strict you would like to give for the chance of mistake under the null hypothesis, then the conclusion would be different. In this case, if you are writing a technical paper, for example, like in your master report or PhD dissertation, in that case, you can say that this is marginally significant. Marginally only means that this level, this p-value is not very small. It's somehow close to the significance level. And if you change the significance level, then just slightly, then the conclusion could be different. That's the marginally significant, the meaning. Beyond that, another thing we would like to do is that whenever you get a significant test, you will always try to produce a plot just to help to see whether this significance really is there in the data. Why do I say it really is there? There are different things that could lead to the hypothesis test result not valid. One is the case that if assumptions are the assumptions do not hold. If assumptions do not hold, then the assumed distribution under the null hypothesis may not be correct. In the chi-square test situation, regardless of testing for homogeneity or test for the independence, we do rely on one assumption. This assumption is that in any of those cells in the table, the expected cell count should not be less than 1. Should not be less than 5. So all of the count should be at least 5 in order for the test distribution to be valid. If any of the cell counts are less than 5, that actually would raise alarm that there might be something that's going to affect the approximated distribution of the statistic. So that's one thing when the assumption may not hold. Another thing that could lead to the people to doubt on the test is sometimes you might have too large of a sample size. In that case, when the sample size is too large, as you learned from the central limit theorem, the more samples you have, the more accurate an estimate would be. Therefore, some large sample size will lead to the tiny little difference being detected by the statistic. And this actually is the case for this example. Here is the histogram of these 4 different education levels in all 4 different neonatal weight gain categories. If you look at this histogram, you will see that they appear to be nearly identical. Identical, that really means that when we consider the education level versus the quartiles Q1, Q2, Q3, Q4, they really do not seem to be depending on each other. So what's happening in this case is that what we obtained is a statistically significant result, meaning that your p-value is less than the significance level. But statistically significant does not always guarantee practically this has an important difference, and this is the case. The data, if we go back to look at the data, for each of the cell, the number of individuals falling into the cell is large. Like, for example, 422, 433, and so on. Because of this large cell, and the total number of individuals in the study is 13,262. Whenever we have a very large sample size, then the small difference could be captured. The very small difference could be captured. So as a result, when you find the very significant result in presence of the large sample size, you would want to double check whether the detected significant result from a statistical test, whether that's practically big enough for you to use it. Like this one, it would be the practically insignificant. So with the difference, the difference among the observed and the expected cell count, that difference is practically not very important. That's the practically not significant. So even though statistically we have a significant result, but practically that difference is not important because the sample size is too large. Okay. So summary for this entire chapter 4 content we learned so far, we consider the two different tests in contingency tables. One is the test of homogeneity. The other one is the test of independence between the row and column factors. These two tests, they have the same test statistic, and they also have the same degrees of freedom and also the same distribution for the test statistic. The only difference is the null hypothesis in the homogeneity is stated as each column's different probabilities in the same column are assumed to be identical. That's in the homogeneity test. And on the independence case, we just say that the row and column factors are independent. Therefore, the cell probabilities, cell ij, the probability Pij could be written as product of the row probability times the column probability. Regardless of the two different hypotheses, we could just use the same hypothesis, the same command in R to conduct the test. And this command is just the chsq.test. And what you provide into the test is the data set in matrix or data frame. As long as the corresponding row and column that needed rows and columns are included in that data frame or matrix, this test will be successful. And it will return you the test statistic value, the degrees of freedom, and also the p-value. Generally, we pick up the p-value and compare it to the significance level. If p is less than significance level, then we reject the null hypothesis. And when p is greater or equal to the significance level, we'll say there's not enough evidence to reject the null hypothesis. So that's all about this chapter about the contingency tables. There are other contingency tables, like so far we have considered just the two-way contingency tables. So the data are the count organized in a table that we see with certain number of rows, certain number of columns. There are other contingency tables, say there might be a third dimension. So you could have a cube rather than just a flat table. For example, consider the admission data, we could have a different major. For example, statistics, mathematics, physics, computer engineering, and so on. These different majors, that's the level of one factor. This factor is the major, okay? And the next factor we can consider is the male versus female. And the third factor that we could consider is a different year, like year 2019, year 2020, and year 2021, 2022, and so on. That's the third factor. So when you have three factors, you have a three-way contingency table. Hypothesis test and the test statistics can be considered similarly like what we learned here for the two-way contingency tables. We will not go into the detail due to the restriction of the time. So that's all for this chapter.